Hey, Algebra 2, we're almost done with a unit. There's only 40 lessons total, and we're on 39. Yay! Today we're going to work on factoring again, and now that we know about imaginary numbers and complex numbers, we can actually factor more things. So I need you to try A, B, and C on your own. You have them written there in your classwork. I'm going to push pause and work on them too, and go ahead and check your answers. Okay, you should be able to do this independently. There's A and B. Push pause and check your work. Just saw a mistake. But I caught it. I'm working on C. Okay, take your time looking at this one. There's a lot of details there, and I showed all the steps, so you should be able to see it. All right? Okay, next we're going to discuss. Hold on tight. Okay, here we're going to talk about patterns and regularity observed. We have 3 exercises that we did, and each one showed a different pattern. So if we were in the class, I would have you talk to each other and we can discuss what the pattern is. But now you just get to listen to my voice. You should be able to come up with a pattern for each thing. So let's see, what were our patterns? It looks like in A we had the difference of squares, okay, which is very exciting. B, we also had the difference of squares. Basically, if we have x plus ai and x minus ai, that gives us x squared plus a squared. Okay, notice how the i's sort of disappeared every time, right? So here we had x squared plus a squared, where x is x and a is I. Nope, a was 1. Sorry. That's how we ended up with x squared plus 1. Here we get x squared plus a squared as an answer, where x is x and a was 5. Now if we look at this last one, we can actually have some fun with it and make it a lot easier, okay? If you look at how it is, we did x minus quantity 2 plus I, and then x minus quantity 2 minus I. We're going to move some parentheses around a little bit, and you'll watch the magic that happens. I have x minus 2 minus I. Let's see. I don't need that one. Too many parentheses. And then x minus 2 plus I. Okay, it's actually much easier now. If I look at this form up here, x is x minus 2, and a is 1, right? So it's easier if I did, well actually let's rewind back here, sorry, x squared plus 25. Here, x squared is a lot easier to handle. It's x squared minus 4x plus 4, and then a squared plus 1. See how it's just a lot easier to handle? And I just moved the parentheses a little bit. It's that commutative property that we learned ages ago, right? Just a lot easier to handle that way. Awesome. All right, we have 4 exercises. Yep, 4 exercises, and then we can get into the problem set. So first of all, factor the following polynomial expressions into products of linear terms. That means into products that don't have squares in them. When it's linear, that means that it's to the first power. Remember, this is quadratic, cubic, quartic, etc. Cool. So this would be x plus I squared, sir, 3i. Let's start over. if we have x squared plus a squared is x plus ai, x minus ai, we can easily factor this into x plus 3i, x minus 3i, right? Same here, x plus I square roots of 5 and x minus I square roots of 5. It's somewhat easier, just a random thought, to write I and then the radical versus radical then I, because if you are a sloppy writer, you'll never know, is this I underneath a radical or not underneath a radical? So if you put it in the front, it's just a lot easier to read. Okay, let's do a little rewind right now. Way back in lesson 29, we learned about conjugates. If we had a radical expression like x plus square root of 5, the conjugate is x minus the square root of 5. And it was a really easy way to get rid of the radical, because if we FOILed it, I'd get x squared plus x square roots of 5 minus x square roots of 5 minus square root of 25. You know, the middle cancels out, x squared minus 5, right? So it was a really easy way to get rid of the radicals, was by multiplying it by its conjugate. You can do that with a plus bi also. The conjugate is a minus bi, because if I FOILed it, let's just have a little fun, a squared plus abi minus abi minus b squared I squared. Middles cancel out. I'm left with a squared plus b squared, because I squared is -1. So the same holds true for complex numbers. There are conjugate pairs, and the product of a complex number and its conjugate pair is a real number. Okay, we have two complex numbers and they are conjugate pairs. Our product of those two are real numbers. Something else I'd like to discuss is just quadratic expressions and how there can be real or non-real complex solutions. So if there are complex solutions, though, if there are complex solutions, you should always remember they will be conjugate pairs. You can have a real number and an a plus bi and an a minus bi, but these will always come in pairs. You can have as many real numbers as possible, but if you get any complex numbers, they're always a pair of complex numbers. For example, if we just look simply at this polynomial equation, okay, we have two real solutions. I can take this one and go x plus 1, x minus 1. So a solution here is -1 and 1. And then here, that just gives me the solutions I and -I. So these are the conjugate pairs, and these are the real numbers. So if I gave you a problem, like a new one, like, hey guys, we know that 3 minus 2i is a solution to the polynomial equation p of x equals 0. Can you tell me what another solution is? Well, yes, Miss Carly, I can. C, if 3 minus 2i is a solution, then 3 plus 2i is also a solution because we know that these come in conjugate pairs. And we are smart. Awesome. All right, let's do one. So consider the polynomial x to the fourth minus 3x squared minus 4, right? What are the solutions? Well, we know that we can do squareds, right? Like I can make this into two binomials that are in squares. So I'm going to do x squared, let's see, minus 4 and x squared plus 1. Let's see, does that work out? Yes, it does. And then I can factor this again. This first one is the difference of two squares, x plus 2 and x minus 2. And then this last one is the I and the 2i, x minus I and x plus I. So I have for a solution, negative 2, 2, we're going to put them in the right order, negative I and I. All right, so those are the solutions. How many x-intercepts does the graph of the equation y equals x to the fourth minus 3x squared minus 4 have? Well, x-intercepts are right there. So if we look at this, it's going to look something like this. It's going to cross the x-axis at negative 2 and 2. So the x-intercepts are negative 2, 0, and 2, 0. Are solutions to the polynomial equation p of x equals 0 the same as the x-intercepts of the graph of y equals p of x? Well, no. The solutions were negative 2, 2, negative I, and I. The x-intercepts were, negative 2, 0, and 2, 0. So they're not the same. Only the real solutions to the equation are the x-intercepts. By comparing the graph of the polynomial to the equation's solutions, you can see that only the real number solutions to the equation correspond to the x-intercepts. Okay, and there's only 2 of them. All right, write a polynomial p with the lowest possible degree that has the given solutions. Explain how you generated each answer. Okay, this first one has 2 real and 2 complex zeros. 2 real zeros and 2 complex zeros. Since the 2 complex zeros are part of a conjugate pair, p may have as many as 4 total factors. So p has a degree of 4. So let's go ahead and work through it. All I'm doing is taking minus 2 and putting it into a binomial, and then positive 3 into a binomial. Then x plus 4i and x minus 4i. So let's go ahead and FOIL away. For the first 2 binomials, we get x squared minus x minus 6. And then for the second set of binomials, remember they're conjugate pairs, so the middle cancels out. So I have x squared minus 16i squared. That gives me x squared minus x minus 6, x squared plus 16. Go ahead and multiply again. This is when things get crazy. I'm going to distribute. So I'm taking the first term and multiplying down, and then the second term, and then the third term. Okay? I'll do this one live, but from now on I'll probably push pause to work through it. So that first one gives me x to the fourth plus 16x squared, and then minus x cubed minus 16x minus 6x squared minus, what is 16 times 96? Okay, collect like terms. X to the fourth minus x cubed plus 10x squared minus 16x minus 96. Check your answers, and we're good. Okay, I'm going to take this one to the next slide. B was -1 and 3i. Now remember, well, let's just look. The polynomial P has one real zero, which is -1, and two complex zeros because those come in pairs. So we can say x plus 1, x minus 3i, x plus 3i. So we know we have a degree of at least 3. Okay, I'm going to push pause this time because you don't have to watch me multiply. Okay, there we go. And we had a power of 3. Let's try the last one. Oh, there's a few more. Sorry. This one we're probably going to have to do on the next page. So, okay, how many zeros do we have here? I've got 2 real zeros and a conjugate pair. So it looks like I'll have a degree of 4. P of x equals, x, that's our 0, x minus 2, x minus 1 plus I, and x minus 1 minus I. All right, if you remember in our opening exercises, we could regroup these to make them a lot easier to work with. So I get x minus 1, that'd be minus I, and then x minus 1, let's see, that'd be plus I. So I get x minus 1 squared plus 1. That gives me x squared minus 2x plus 1, x squared minus 2x plus 2. Okay, now let's go up here. I didn't do anything with these yet. That gives me x squared minus 2x. I'm going to go ahead and bring that down here. Now I need to distribute and multiply. So I'm going to push pause because, again, you guys don't have to watch that. All right, there we go. It shouldn't be surprising that we don't have a constant at the end because we had the x equals 0 at the beginning. Cool, but we do have a degree of 4. Okay, so that was C. Let's go ahead and try D on the next page. For D, we had square root of 2, negative square root of 2. There's our conjugate pair. 3 and 1 plus 2i. Okay, so here I have one real number, this conjugate pair, and I need something to match this one. So I would have 1 minus 2i. So I've got 1, 2, 3, 4, 5. So I should have a degree of 5 at the end, right? Okay, this one's going to be fun. Let's go ahead and write them all out. X minus square root of 2, x plus the square root of 2, x minus 3, and then x minus 1 plus 2i, and then, oh, another parenthesis, x minus 1 minus 2i. Okay, we can do this first binomial, x squared minus 2, x minus 3, let's go ahead and get that out of the way too. That gives me x cubed minus 3x squared minus 2x plus 6. Okay, now for this part. I'm going to have x minus 1 minus 2i times x minus 1 plus 2i. X squared minus 2x plus 1 minus 4i squared. That gives me x squared minus 2x. This would be a plus 4 plus 5. I need to multiply these two polynomials, and now I'm going to push pause. Okay, there's just no need. You guys can distribute things, and I'll show all of my work, and you can check it and make sure you get it right. All right. Oh, I forgot to cross some things off. There we go. I made one mistake and wrote it in red so that you all could see it. Okay. Yep, there's one more. Amazing. Okay, it's smaller. How many degrees will we have here? Well, it looks like we have two solutions, but they both need conjugate pairs. So that just means I have p of x equals x minus 2i, x plus 2i, x minus 3, oops, that's messy, x minus 3 minus I, and x minus 3 plus I. Okay, let's do a little math. That first set gives me x squared plus 4. On that second set, let's go ahead and rewrite it a little bit. I get x minus 3 plus I, and x minus 3 minus I. So I have x minus 3 squared, which gives me x squared minus 6x plus 9. And then, remember the middle cancels out, so this would be minus I squared. So that would be plus 1. So I have x squared, that's messy, x squared plus 4 times x squared minus 6x plus 10. Let's go ahead and do some math there. X to the fourth, I'm just distributing, minus 6x cubed plus 10x squared plus 4x squared minus 24x plus 40. Collect some like terms. I usually cancel things out as I go to make sure I don't make any mistakes. Squareds. It's easier on this one than it was with the last one, right? Check my answer. Looks good. Okay, a little summary. Polynomial equations with real coefficients can have real or complex solutions, or they can have both. If a complex number is a solution, then it has a conjugate pair. Real solutions to polynomial equations correspond to the x-intercepts of the associated graph, but complex solutions do not. Excellent work today.